Thank you very much for having me here again. It's always fun to visit Davis. So I'm going to talk about precision probes of new physics with nuclear and atomic physics. This is sort of work I've been involved in the last couple of years that I think has got me pretty excited. So obviously the standard model is true. We've established that through a bunch of colliders over the last 100 years or so. The challenge though is that even though the standard model has withstood every direct experimental test we have lobbed at it, we know that it's not a complete theory of the world. It's not just speculation. There's actual observational facts that the standard model does not explain. There's more matter in the universe than antimatter. Moreover, if you take the laws of nature and you turn the clock back and go back to the very, very early universe, we know there's a point where general relativity breaks down. And so clearly there's some new physics that explains why the universe itself bothers to exist. We also know there's a new particle out there called the dark matter, whose properties we don't really understand. There's also dark energy, which clearly exists in the world, but again, we don't exactly understand either its energy scale or what it could really be as well. And then we have theoretical problems with the hierarchy problem. Right? So this is concrete evidence that there's new physics out there. It's not just speculative. The challenge, though, is understanding what this new physics actually is. Now, what we've done experimentally in the last 100 years, we've been looking at how colliders can help us understand what this new physics could be, is that we have probed physics at high energies. But if you generically think about what this new physics could be, and you ask the generic question, what is the mass of this new physics, and how does it interact with us, is really a two-dimensional plot. Right? I can go up in energy, or I can go down in coupling. And colliders basically move horizontally in this two-dimensional plot. Basically, we are probing higher and higher energy, but the couplings we typically probe in a collider is relatively big. Right? They're not super small couplings because you need statistics as a way to probe really, really weakly coupled particles. In my opinion, there is considerable reason to think that we should actually go down in coupling as well, not just up in energy and see what's out there. And I would say that if you think about our typical sources of new physics that we know exist, like for example dark matter and dark energy, and this is of course old physics, but of course it's something very important to do, like gravitational waves, these things do not necessarily imply that the answer to these questions lie at high energy. They're really telling you that you want to probe weak stuff. So the question really is to ask, given the strong physics case that exists in order to probe very, very weak couplings, how can we actually do this? How do we build the next set of experiments which will really be looking at not just going to high energy but also into very, very weak couplings? What can you actually do to do that?
So it's a weak physics case.
It's a very good weak physics case. Exactly. So what you really need in order to go to weak couplings is basically need one of these three kinds of ideas in your experimental setup. To overcome a weak coupling, you either require high statistics as a way to probe weak couplings, or you need some kind of amplifier in order to make some small effect large, or fundamentally you require some kind of quantum sensing, presumably, to be able to get the precision that you need to go after weak couplings. And I'll talk about three experiments today, and they will in some form or another make use of one or all of these kinds of ideas as a way to probe new physics. So I'll talk about these experiments. The first will be an experiment called the Gandhi experiment. Okay, it's a way to use nuclear physics to probe very weakly coupled particles. Then I'll talk about two dark matter experiments. One is something called a magnetic bubble chamber, which is a way to detect sub-GeV dark matter. And then I'll talk about how one can use something called directional detection with NV centers to go after just WIMP dark matter below the solar neutrino floor. And I'll conclude. So I'll start with the Gandhi experiment, and this really stands for Gamma Nuclear Decays Hiding from Investigators experiment. And that is basically because this is a peaceful application of nuclear physics, and we figured Mahatma Gandhi would approve of a peaceful application of nuclear physics. And we're actually building a proof of concept of this right now with Rupak Mahapatra at Texas A&M. But these are the people who were involved in sort of conceiving it initially. With my theory postdoc Hari Ramani, well, Giovanni Bonato and Alexei Drobyshev are experimentalists. But Rupak is a guy taking it forward because these two guys are postdocs. So here is the basic idea, okay, just the overall picture, which is that we're going to start with some radioactive nucleus A, and that's going to decay in what's called a gamma cascade. So A will typically want to decay through a beta decay, let's say, and instead of going to the ground state of nucleus B, it happens to go into some second excited state. And the second excited state promptly decays to another excited state, which then promptly decays to the ground state. Right? So the initial decay from A to B to this state is some pretty long decay. Okay? It's a beta that takes a while. But once it populates this level, these two gammas are prompt. And what we want to do, the idea of Gandhi, is that we want to tag the first gamma, so we know that this level was populated. Right? So the beta decay happened, so the first gamma, so you know this level was populated. And what you want to ask is basically, did you also see the second gamma? Right? Because if you did not see the second gamma, presumably a new particle was produced in this process, and that would be a sign of new physics. And so that's what you want to do. Tag and make sure that you absolutely saw everything else, so that you did not see the second photon, would be a sign of new physics. And the question we want to ask is it possible to build a protocol for this kind of experiment where a single event would tell you that you discovered new physics? And the question becomes, how many events can you actually process to actually do this? Right? So obviously, if I, with my fingers, can do, well, the good clock can maybe do, a few per second or something like that. But with a really good technology, how many can you really do per unit time?
Right. For the single event for discovery, I mean, if you found a single event, you claim 5 sigma discovery.
You claim, maybe you saw 5 events, you should claim 5 sigma discovery, something like that. Okay. That your probability for missing something is so small. Okay. So the question we're asking is, how well can we do? Right? What kinds of technology would you want to think about? And in terms of the new physics we will be sensitive to, we're of course looking at transitions in nuclear physics. So we're looking at new particles that are coupled to nuclei. Right? So we're looking at baryonically coupled particles. And since they have to be produced in these nuclear decays, we're basically looking at particles whose mass is below an MeV or so that they can be comfortably produced in this process. So let me tell you the concepts of the nuclei that we have in mind, the setup we want to build, and what kind of theory you will be testing. So the main issue for the nuclei that you want to use, what we considered was basically lifetime. So the parent nucleus that you're trying to use, the nucleus A, has to be relatively long-lived so that we can actually handle it. Right? And then we want a pretty high cascade efficiency so that when A decays, it dominantly does what we want it to do. And then we also want it to be available. Right? So it's a nucleus, the parent nucleus, something that we can easily get in significant quantities so that we can actually build a real experiment at high statistics. So those are the considerations that we had in mind.
Also, I mean, you somehow want to know that you weren't fooled, that there's some other, that there's some kinds of decays that give you the first gammas and don't give you the second gammas.
Right, so there's some simplicity kind of thing.
Different nucleus or some kind of weird...
Yeah, we didn't want too complicated a nuclear set of decays as well.
So we're going to talk about those kind of more, whatever, theoretical...
There are some others, there's some of the nuclei we considered that have a more complicated chain of events.
Yeah.
But, so I won't quite talk about them here. But like basically, in all of those ones, there were certainly handles that you could use to make sure that you got what you wanted to get.
I guess anyway, that only becomes a real issue if you find a signal, if you're so lucky to find a signal.
Exactly, yeah. So then you may worry about other nuclear states. Maybe.
Then you can change your nuclei and do other things.
So as long as things are prompt, I think they're okay, is what I would say. Right. So the first example we considered a 6-day cobalt, which in 5 years, a lifetime of 5 years, decays to nickel 60, and it mostly goes to the 4+ state of 60 nickel. At which point, everything after this is very prompt. So even if you had a series of other nuclei, they would just kind of mess up what we think our signal is, but we will still see the energy. And that's what we will harp on as a way to do what we want to do. So what happens is that basically you, with 99.8% probability, you go to the 4+ state, which with the 1.17 MeV goes to the 2+ state, and then to the 1.33 MeV goes to the 0+ state. Okay, that's what it does. And this will turn out to be a little bit of a problematic situation. We won't be quite able to do everything we want to do because of the fact that the two gammas are similar in energy, so you may often confuse them. So that's an intrinsic background with Cobalt 60. But we just studied it mostly because of the fact that we have it's available relatively easily and it has a pretty long lifetime. There's another system that we like better in terms of how much it can probe, but it's much harder to deal with nominally, which is with sodium-24. And sodium-24 has a lifetime of about 15 hours, so it's not super good, but it's also not super bad. Okay? And with 99.85% probability, it goes to the 4+ state of magnesium-24, which with the 2.75 MeV goes to 2+, and a 1.37 MeV goes to this. Right? So the main thing we want to harp on is the fact that, look, these decays, once I populate this, right, are prompt, and however they go to the ground state, they have to give up all that energy. And the question we're going to ask is, how easy is it for you to actually miss a 1.17 MeV gamma or a 1.33 MeV gamma? Right? Because those are like a lot of energy that you're dumping in the system, so you want to identify those with high fidelity. That's the question we want to answer.
The thing is, Mark, especially, you do have to worry about the background of 1.17 MeV, where is from some other process where you're not populating the 2+ level.
Yeah, so the thing would be basically that, this initial state, this decay happens. Let me talk about that in a couple of slides so you will see it better. Okay.
Can I just comment? Everyone should know that the isotope on the left is specifically what CS Wu used to show parity violation to weaken correction.
Okay.
Cobalt to nickel.
Good to know.
So let's use it again.
Let's use it again. Maybe we'll find something else. Right.
Another Nobel Prize.
And if you just look at the parity of the states, for this particular process that we talked about, you're going from 4 plus to 2 plus, 2 plus to 0 plus or whatever. So the parity means that you're reprobing scalars and vectors in this particular process. And not pseudo-scalars or pseudo-vectors, because they have the wrong pair. So how do we propose to do this? What's the setup? Right? Here's the main idea. So I'm going to take a scintillator, okay, a big piece of scintillator, and I'm going to put my radioactive source in the middle. Okay? And that's going to have these decays. And these guys are going to go out there, and as they go out there, they'll produce a bunch of photons, which you want to measure. Okay? So the goals that we set ourselves, and see how well we get there, is basically ask, can we probe a branching fraction of 1 part in 10 to the 11, which would correspond to, say, something like 1,000 events per second. Okay? And are you really sure that you'll be able to capture all the gammas in this process? And we ask eventually, could we get as good as 1 part in 10 to the 14 branching fraction, which corresponds to a megahertz or so data taking rate? Is that eventually possible? Is that possible or not? So what we really want to do is to ask, can we really observe every event at the individual level? Right? That basically, when one event happened, for that brief period, I know the event very, very well, and therefore I'm not confused by something else going on. So I basically say that I want to have some technology which gives me, which permits me to handle a very high event rate, so that in that time when the event actually happened, I'm very, very clear about what actually went off. So I'm going to propose that we use either a plastic or a crystal scintillator, because these are scintillators that essentially respond at the nanosecond level. So the way I'm thinking about this event is to say that something went off, right? And in that 1 nanosecond, I know that the entire system decayed to the ground state. And I want to collect all the energy that came out in that 1 nanosecond as a way to handle the kind of questions that you asked. Because even if you went through a complicated set of decays, all of those will produce a bunch of energy, and that energy in a scintillator will come out some way or another.
But you have no way to know when your source triggered.
You will know basically because of the fact that when the source goes off, there's a beta that happened. Okay? So let me get back to you in 1 second. Okay. I'll tell you what the protocol we have in mind is. So of course you want to kind of contain all of these photons in there. If the photons leaked out, obviously you would be in trouble. Okay? And so just in terms of the number of mean radiation lengths that you need to contain all these things, you require something like 30 radiation lengths, okay, to contain all of that. So this could be a challenge in the sense that if you think about plastic detectors, the radiation length is relatively long, the mean free path is big, so thinking about something like a 10-meter size plastic scintillator, that's of course a lot of real estate, but I'm told that these are cheap to make, and one can actually get large modules at relatively low cost. Crystals are harder. Okay, they have they are good in the sense that they have a much shorter mean free path, so you only need about a couple of meters or whatever of this stuff to contain everything, but they're harder to grow and could have more challenges. But in the proof of concept that we're trying to build in Texas A&M, what we're actually proposing to use are cesium iodide scintillators. See what would actually happen. So here's the protocol to answer the kind of question that you asked, which is the following thing. We want to think of this detector really as a segmented detector, where we have an inner module, okay, and an outer module. The job of the inner module is to really identify the event very nicely so that we know what's actually happening. Okay? So we place a source inside with whatever activity that we want, which could be, 1 per millihertz, or 1 per a kilohertz, or 1 per megahertz, right? Some source that we put in there. And then our radioactive thing goes off, right? Something happens. As it goes off, in the inner module, we require that the gamma that comes out deposits all of its energy in the inner module itself. Okay? So something happened in there, there's a beta that we see in here that's consistent with what we expect, and we see an inner module gamma happening as well, right? So in the same nanosecond, when this beta went off, we required this photon to have come out and deposited all of its energy in that particular region.
How do you observe the beta activity?
Oh, there'll just be like some, so we require both a beta trail, like there's some scintillating light coming out of it, as well as the photon that's coming out. So I don't know exactly that it's a beta, but it's something like I know that there is a electron trail coming out of it.
And how are you sure that they will be separated in time?
Well, you know that the decay happened quickly, right? So once you have the beta decay, you know that the lifetime of that state is like a picosecond.
So what I'm saying is that might be merged.
Yeah, so if it's merged, we will ignore the event. So we could have required that basically that I saw a nice beta in one direction and a nice gamma as well. If that did not happen, I will ignore that event completely.
Okay, so you're killing your statistics.
Sure. I think it's unlikely that that will happen many, many times, right? That the beta and the gamma will exactly be on top of each other.
Why? If it's so fast, it will. What's the speed of your detector?
Well, the thing is, I'm requiring spatial separation, right? That I don't expect the beta. It's true that the beta and the gamma will happen basically the same time period.
So you want the position
Resolution, yeah, yes. At the centimeter style level, that you require the beta to go in this direction, and you want the gamma to go in some other direction. You require that. Okay. So that needs to happen. And then you're going to require that in that nanosecond, there was no other energy deposited anywhere in the entire detector. Right? If there was any other energy anywhere in the detector in that nanosecond time scale, then we throw out the event completely. So we're going to ask what are the intrinsic backgrounds that we can't overcome in this particular process if this kind of technology can be engineered.
So we didn't say what the outer modules were for.
The outer modules are simply there to make sure that you didn't miss the second gamma. Sorry. So basically you saw the first gamma, right? So we're very sure what happened was, yes, there was a beta on this side and a gamma on that side.
Right.
Okay.
There's tiny probability to miss the second one.
The second one, exactly. And that's why you need the large number of outer modules to avoid that tiny probability. Okay. So the question is it possible somehow for the second gamma to fake the first gamma? If that happened, we would be in trouble. That would be an intrinsic background. And there is an intrinsic background for Cobalt 60. So let me first put up a straw man. This will not really be a problem, but the next one that I talk about will be a problem. Okay. So the main issue is that we have finite energy resolution, right? So a 1.33 MeV gamma is very close to a 1.17 MeV gamma. So it could be that, let's say, the first decay happens, and you produce them both at the same time, which will happen, obviously. You produce the 1.17 MeV and the 1.33 MeV gamma. So if I confuse the 1.33 MeV gamma for the 1.17 MeV gamma, I might think that I'm sort of producing my events even though I'm not. But of course, when that happens, right, it's highly unlikely that the signal will come with, two 1.17 MeV gamma at the same time. So I can just say, like, look, I only want 1.17 MeV gamma at a time. When that happens, obviously, I can just completely eliminate this particular background. But the other background that I talk about will be a problem, which is that with a small probability of 100 minus 99.88%, my 68 cobalt will go to this 2+ state. And when it goes to this 2+ state, it could be that I have a very soft beta, okay? And that very soft beta could happen at the same time with this 1.33 MeV gamma happening. And this 1.33 MeV gamma may have a very, very soft Compton in my inner module. And when that happens, I might mistake this soft beta and the soft gamma to be my 1.17 MeV, to be the initial beta. And then the remaining 1.17 MeV gamma just goes outside and does some kind of scattering, right? So that might make me think that, oh, this soft beta 2+ and the soft Compton gamma becomes the initial beta, and what I got remaining was a 1.17 MeV before, right? So that would be a background that's a problem.
So I think a little bit. Why the second beta is soft than the first beta? I thought that this energy is larger than the first energy.
It is, but a beta decay means that a bunch of energy goes to neutrinos, right? So the neutrino could exactly go carry off enough energy that I basically think that this beta, right, even though it's more energy being released overall, most of the energy is carried to the neutrino.
Oh, okay.
and most of the energy is carried with the neutrino, this can go somewhere out here, right, in terms of the energy in the beta itself.
I understand, sir.
Yeah, exactly. So that's an intrinsic problem. Okay.
What's the typical energy on the beta and the energy difference between the
Oh, it will be whatever this is, right? Like the ground state to whatnot.
before just a cobalt?
Oh, that one I don't remember exactly, but it's a few hundred keV or something like that.
Why cannot this directly go to the 0?
But that's okay, right? We don't really care about that. Yeah. Because I remember I'm going to require that I actually get this 1.17 MeV to tag what's going on. Okay. So that's one thing you may worry about. The second thing you might worry about is that you might populate this guy with a soft beta, right? And then somehow this guy did the right thing. It produced the 1.33 MeV gamma to go to the ground state, but because of bad energy resolution, I might mistake this 1.33 MeV gamma to be the 1.17 MeV gamma, and then I'm again screwed. Okay. So how do we handle this? This is the kind of geometry that we thought might be interesting to probe. The main idea is that we want to kind of separate the detector, okay? Because we're already taking a bunch of space, so why don't we just make it a little bit bigger in order to do what we want to do? So let's say I make this inner module somewhat big, right? And that basically means that this beta and the gamma that are coming out are going to be separated geometrically, right? And that's an important thing to handle the kind of question you asked anyway, okay? So the confusion that we will have, that these two things happen at the same time and all these things happen, is really only if both the beta and the gamma go in the same solid angle. And we believe we can do centimeter scale position resolution. Okay? And so that gives you some suppression of this background, right? In terms of asking that both these things go in the same solid angle. So then you put in the factor that the number of times you really get the soft beta as well as the soft gamma, and the fact that you populate the bad state is only about 10 to the minus 3. You put in all those numbers, roughly the simulated reach for how well we can do is about 10 to the minus 11, it turns out. And the really only way to actually eliminate this would be to make a bigger and bigger detector, but at some point it becomes more and more ridiculous, but then you gain in solid angle essentially. So that's what you'd have to do. Interestingly, this background does not exist in sodium-24, because in sodium-24, the first gamma is much more energetic than the second gamma. So there's no way the second gamma could actually fake the first gamma. The second issue you worried about is energy resolution, right? There is a soft beta to 2+, and then you worry about a mismeasured energy, right? So then you ask, well, how good is your energy resolution actually? And that is set by the light yield of your scintillator, as well as the quantum efficiency of the photodetector. Okay. Furthermore, you also will lose some number of photons in your scintillator because it gets absorbed. So we put all of those factors in together. So we took classic scintillators from like 1,000 photons per MeV of energy. PMPs are something like 0.25 of Q, and we also assumed a factor of 3 loss in the photons that they get out. Yes.
I thought you said you were going to use cesium iodide.
Oh, so this is what we did for the paper. For cesium iodide, the number will be different, and the appropriate number was put in. Okay. So then a formula is something like this, where you basically say, well, my uncertainty is the square root of the number of photons I expect to see. Okay. So again, with cobalt, we think this background roughly kicks in around 10 to the minus 11, okay, in branching fraction. But again, it's absent in sodium-24 because the two gammas are very, very different in energy. We talked about a number of other backgrounds. They don't, they require engineering and work. Obviously, I'm not going to do this, so I can be happy about it. But the experimenters who build it have to think about it carefully. One issue one might worry about is something like a detector dead volume, is the fact that perhaps, for whatever reason, some part of your scintillator decides to die. Okay, so people have studied this quite a lot, and these are typically at the 10 micron length scale. Now, the gammas and the betas that we are interested in, they typically travel over a centimeter, so it's unlikely that they will lose a lot of energy in just that 10 micron region to really be a problem. We have thoughts on how to calibrate this system, just so that we don't fly in blind. So one interesting thing that could be done to see if this entire program makes any sense is that we could actually put in a source of positrons in the system. Okay, if you put a source of positrons in the system, the produced positron will, of course, move a little bit. It looks a lot like what we're talking about, and then annihilate with some electron in there and produce two gammas. Right? So we can basically ask if in our particular detector we always get two 511 keV lines when we actually have a system with positrons in there. You may ask, could the new physics also not happen the same way, right? Because we talked about, in the case of the new physics, it would be E plus E minus annihilating into, say, a single photon and some new particle phi. So here is where a little bit of particle theory becomes useful. It turns out that couplings of electrons to light fields are highly constrained by supernova, red giants, white dwarfs, and all these things. That essentially at any of the branching fractions that we are talking about, there is no way that an electron would annihilate with a positron and produce a missing particle without being afoul of those bounds, while this exists for nuclei. So this becomes a way in which we can actually calibrate the system in situ, where we have both a positron source as well as this nuclear source we're talking about, as a way to kind of make sure that this detector is doing what we expect it to do. Okay. We also talked about radioactive contaminants. If you had some stray radioactive thing somewhere, right, and it produced a beta at the right energy, so you got confused, and also produced a gamma at the right energy, so you again got confused. So for sodium-24, we looked at the list from new data, whatever. We didn't find anything that was relevant, that was going to be around for a long enough period of time for us to concern ourselves. But for Cobalt-60, we do have potassium-40 that is known to exist in some plastics, but not all, perhaps. Again, I don't know the answer to this in sodium iodide. But, again, this background more or less came into the same level as around 10 to the minus 11, so we didn't really work hard to worry about it. And of course, you worry about cosmic rays, and the main thing is that with our sort of idea of how to do this, we're going to demand, as he said, a very, very clean event in the inner module, and if anything happens anywhere else, we veto the event, right? So we think the same thing should also actually handle cosmic rays as well, because if something else happens at the same time, throw it out. And you might worry about the fact that maybe a cosmic ray comes in, it does something somewhere here, and some neutron or whatever goes in and does some damage to you. This, of course, can be calibrated by just putting the source in and the source out and seeing if you got some weird event in the inner module, right? But what you really want to rely on is the fact that there are many, many radiation lengths that separate the inner module from the outer module. So whatever is going on outside will probably keep the inner module safe. But again, this can be calibrated. When you build your actual setup, you want to make sure the inner module is as clean as we think it should be, right? Without the source.
So for the cosmic ray background, what's the rate of this background?
What is the what?
Rate. How many events you can usually expect for the cosmic ray?
I mean, remember, this is it's not really a serious concern, it turned out, basically because we're interested in timing at the nanosecond level.
Okay.
Right? So that is what really helps you cut down on a bunch of these things.
But again, to time at the such a nanosecond level,
Yeah.
you can only do it like if you are an accelerator somewhere else, you know when your source triggers. Here is like radioactive decay, it's just going to happen, as all other radioactive decay. You're just going to go and take your data. So it's not clear to me you can just simply state it like that, because you don't know where you say now my whatever now.
Well, the occurring of the event is the fact that I'm actually seeing the 1.17 MeV gamma, right? So that's something that I collect.
But 1.17 MeV gamma might come from a Compton scatter of a higher energy gamma, or might come from the two gammas from the other. I mean, you have plenty of opportunity there, because all your scintillators, whether they are sodium iodide or plastic scintillators, are very radioactive. And I mean, very radioactive for these levels.
But in the sense that, yeah, so anything that's happening in the outer module, if any event energy occurs at all, I'm throwing out the event, right? So it only really comes down to the fact that...
From your detector material.
That's what I'm talking about. Right, so anything in the outer module, if anything happens at all, I agree with you. I won't bother to even understand what's going on. I'll throw the event out
But
completely.
you have a lot of volume and a lot of mass in your inner volume.
Yes.
That's like a lot of radioactive nuclei. They're intrinsically sitting.
Right, I agree with that, right? So you will see, if anything at all goes on that you don't really understand, I just throw out the event. So something goes on, let's say you get, 1.17 MeV gamma with something else happening. Fine, I'm throwing it out. I have no problem with that.
So maybe just, if you ran sort of the same amount of time, roughly, the same amount of time, empty is full, you can just measure that
It doesn't have
background.
empty influence, it's a plastic scintillator.
No, without my source.
With source, without
With source and without source. So I can confirm my prediction.
Yeah, but then I
Then
don't
you
think-
measure the sum of
Sure, but I
cosmic
don't
rays
think
and
then you are
radioactivity.
getting like, in a background subtraction. I don't think that you reach this precision.
No, I think it is, I mean, from what we could tell, right? So if I did sodium-24, for example, there's a 2.75 MeV gamma. I mean, if you really want to just get that and nothing else, right? It seems to me that at least from the contaminants and all these things that we found, there was nothing really there that you think about it.
If you take a look at the background of
Yes.
any
Yes.
low energy experiment,
Yes.
so in any dark matter experiment,
Yes.
or neutrino is double decay,
Yes.
you will see that there is a background there. Now, I mean,
It has to be at that very narrow energy band and nothing else.
I mean, I think.
no, because your resolution is poor.
Right, so
I think,
So
what- I
it's
mean,
not
is it- I
very
think what
narrow,
you're,
and also like
It's-
time-wise,
it's-
it's
it's
also
about-
not very narrow.
it's about 100 keV is the, I think, sorry, cesium iodide, I think it would get 30 keV.
I think it's weird.
No way you can get 30 kV. And your photomultipliers are not nanosecond. I don't know which photomultipliers you're going to get, but they are not 1 nanosecond.
No, our event rate is anyway not at a nanosecond, right? We're talking about either at the kilohertz level or the megahertz level.
Okay, that's fine.
But they happen.
No, but what I want to say also your, whatever, your timing. I mean, I think you are also quite optimistic of putting the timing, like, for whatever, so both energy and both time and your position resolution of 1 centimeter in the plastic.
Well, I mean, so I can only tell you what the experimenters we talked to said was possible. I'm a theorist. But it seemed to me that from all the people I've talked to there, they didn't think any of this was that absurd.
That's not really an answer, but okay.
I mean, I can't say, I mean, it's hard for me to judge that part of the question, whether or not they can actually get a centimeter, and I mean,
Yeah,
as a
but
th-
that's, since you're proposing, that is your job.
no, it's sort of, I mean, I trust the experts on that particular thing, where they say, yes, if they believe that you can get centimeter position resolution, am I really going to be like, no, you cannot?
That's also not a pure theorist answer. I mean, you have to criticize everything, you know?
Well, I've talked about this to a number of people there, and they do not blink at these statements, that's all I can say.
Okay.
Have they shown you plots?
They have not built the experiment, no.
No, simulation plots.
So, you know, well, the simulated stuff was done with using Geont. Okay,
Sure.
so that is where that was done. Yeah. Okay. And really, once again, you know, my hope for this really is the fact that when I simply have a 2.75 MeV thing going on, and I'm really demanding nothing else happens.
I mean, theoretically, like, in a sense, like,
Yes.
ideally, yeah, I see your point.
Yes.
but I think there are a lot of experimental effects there that are somehow, at least in my naive opinion,
Yes.
not being taken into account.
Okay, I mean, you know,
Yeah.
yeah, I mean, I think like it's a question anyway that before we move forward and put the actual whatever thing in there, it's certainly something we can just stick it in there and ask.
you would like to see things like, for example, just simulated plots that would show detector response and things like that.
There are a lot, like, for example,
Exactly.
like he's saying, like, about this,
Because, I mean, maybe-
like, containment and then efficiency for all this. You start cutting, so you might end up, like, having a really, actually small efficiency for your good signal. And so then that means you're actually somehow cutting your signal rate, and then also the background can come in. So there are a lot of things that can be.
I mean, I mean, what might be useful, maybe, you know, for them, maybe, is be to say, what plots would convince you? Because if they can make those plots, that would be interesting, and it might be good, you know.
Yeah, I'm certainly
useful
open
for
to
you
hearing
know, like,
suggestions
what-
for.
What exact, you know, what things would you want to see, at least at the simulated level, and then
How about take a look
validate
at
it?
what the experiments already do, because they do have a Cobalt 60.
So,
they do have a Cobalt 60.
Giovanni Benato, who is part of the person who
Yeah.
proposed it, he is a postdoc at, what is that big, Borexino? And then I think he worked on,
Yeah, in a sense, like, one can access
yeah, so
those limits.
so these two guys who did this stuff, Alexei Drobisev as well as Benato, are people who are in these large scintillating experiments.
Yeah, but what you can do, you can go and extract the data, and you're going to have a poor efficiency because those detectors are not as optimized as your detector, but still, they use scintillators and they use PMTs, and they can have a Cobalt 60 as a source, not the other.
Yes.
And so one can access from those data what one can do, and then you go ahead and you say, well, I'm ramping up this efficiency.
That
I'm
is certainly a
going
good way to
be
move
better.
forward. That's certainly a good way to move
That
forward.
would be probably more convincing.
Yeah, I mean, I'm not asking you to give me money right now to do the whole thing, right?
I don't
But it's
have
sort of,
money, so it's
but
fine.
what I can say is that the people who actually work in that area, who is Benato and Drobisev, and I imagine are aware of what they actually see when you run a scintillator. I mean, they seem to think that this was not insane. It requires work, no doubt, but nothing about it per se screamed impossible.
I don't know, I have been trained to be critical of what.
That's a good thing to be. That's a good thing to be.
fine.
That's fine. Yeah. Okay. So in terms of the triggers itself, at 10 to the minus 11 branching fraction that we are talking about, the trigger rate is something like 1 per kilohertz. That is not as hard as the LHC. While at 10 to the minus 14, we have something, pretty high trigger rate. That's something that something like LDMX would actually try to do. Okay. In terms of the theory of what we can actually try to reach, we just had a simple model just to construct something and see what actually happens. We have a scalar, for example, coupled to protons, for example, and that's a mass. Okay? And in terms of what we're trying to do, we are looking at a branching fraction in some E2 transition. Thankfully for us, Maxime Pospil have already calculated this thing. So there it turns out that the branching fraction of producing the new particle phi in relation to a photon simply scales as the couplings, and that is basically what we will be using. Okay? And what we want to really rely on is the fact that there are really poor constraints on baryonic forces above 100 keV or so. And this is interesting because of the fact that a number of light dark matter experiments out there today that are basically making use of this hole and using these as mediators, for example, in terms of what can happen. And I also have a belief, it's actually kind of even true, that if you had a new particle at this scale of energy with the kind of couplings that we're interested in looking at, right, these could in fact cause type 2 supernovae to blow up. As you may be aware, there has been a very difficult to make type 2 supernova blow up in simulations because the neutrinos just don't seem to get it. While if you actually have a new particle at this level, this could be a new way to carry energy within a supernova and potentially cause it to blow up. So this is our estimated reach for what we can do, right? For Cobalt, we certainly have a background which prevents us from getting deep in coupling range. While for sodium-24, we don't think that's actually the case. In terms of new physics that we can actually probe, this is the coupling GP as a function of mass over here. And the rough ball game here is that if you are solely asking what are limits on new particles coupled to protons, then those are actually turn out to be pretty weak because it's hard to probe a proton very well because of electromagnetism. So those limits are somewhere up there. Okay. But then if you're more honest and you say, let me UV complete the model, and if I UV complete the model, this coupling to protons will also couple to pions and things of that sort. So there are certainly limits from rare pion decays and rare kaon decays and stuff like that. Okay, so you really want to beat those. And to beat those, you're required to do something like 10 to the 9 decays in a year, which corresponds to 100 decays per second. And then you can try to get more and more aggressive. And our most aggressive reach we think we can get to is potentially 10 to the 14 decays. That would basically cover the entire parameter space between where there are limits from lab experiments like kaon decays to where if the coupling is smaller than this amount, then the particle will escape things like supernova and cause cooling. So we can basically cover the entire what is called supernova crack or something in terms of new particles. And this is of course the region where a lot of people try to build models for dark matter and all these kinds of things.
What is the HB star?
Horizontal branch star. So these are stars that can also cause cooling. Okay. Just an example of what you could try to do for dark matter, for example, is that you could simply take in your mediator phi, okay, which is some new particle. It's also the case that one can think about a light dark matter scenario where instead of decaying into the particle phi, I just go into chi and chi, right? So it's just a mediator that sort of decays into dark matter. Obviously, the same decays can also do that, and then you're able to probe a bunch of parameter space there as well.
Why do you have that sharp?
Yeah, you mean like these? Oh, so that has to do with how the bounds move around, really. Okay. So what's interesting to me in the story is that the fundamental limit here is not set by the availability of the source, right? So usually if you're trying to produce light particles, what limits you is the statistics at which you can produce a source in a collider or whatever. You just don't have enough collisions even going on in order to produce them. But over here, you can go and buy a radioactive source that's say a microgram, right? It's very, very active, of course. But you fundamentally have the ability that with a microgram of this radioactive source, you can have like 10 to the 19 or 10 to the 18 decays in a year, right? So in principle, that's a very, very high rate, okay? It's comparable to, for example, what I believe is being done for mu-E gamma style experiments nowadays. You get like very, very high rates. And when you have such a high rate at which you're actually doing these things, it is possible, at least theoretically, that you produce a new particle in the lab, right? Which is almost unheard of when it comes to probing these very, very weak particles at very, very low coupling. Of course, at very, very high event rates, it's very, very complex to handle any of these things. But I'm interested in this story mostly because of asking if technology is pushed in this direction of very, very high luminosity and very, very high rates. It seems really possible, at least in principle, one can think about ways to probe for these very, very weakly coupled particles past the supernova limit, where it'd be really interesting to do stuff there. That's all. Okay. So the really hard limit, more or less, turns out to be something like trigger electronics, because it's hard to really probe particles at this very high rate. Okay, but hopefully that would improve with computing power and stuff like that. Okay. We've also thought a little bit about better nuclear levels. Is that something that one could actually make use of? So one of the things that we're exploring actively, and it seems very interesting, is 90 niobium. So in 90 niobium, there is actually a particular chain of decays where the final state actually ends up producing E plus E minus. It goes through whatever is called internal conversion or something. At which point, what you're talking about is that if you want to miss whatever is going on, you really have to miss a bunch of gammas as well as an electron and a positron that goes up. Right? And the electron and the positron will continuously lose energy as they move out, and the positron will also annihilate with an electron to produce two 511 keV gammas. So that's at least a complicated set of decays going on in there, but it seems very interesting in the sense that you're just making sure that the standard model channel is much more visible, because instead of just producing one gamma, you're producing a pair. Okay, and if one can actually use 65 cobalt, it also has a complicated decay to 65 nickel. One could actually look for axions doing that, because there the parity levels are much better matched. Okay, so we couldn't probe axions in a current set of stories, basically because of the fact that parities of the level are not good for axion emission, but you want an M1 transition for an axion. That's something that exists with 65 copper going to nickel. So let me move past this topic and talk about magnetic bubble chambers. This is an idea that I've been involved in now for the last couple of years and now. And this is currently being built in Texas A&M with Rupak Mahapatra as my experimentalist colleague. There's a bunch of people actually involved in the whole story. And let me tell you what it's about. Okay, so let's look at the story of dark matter. If we look at the story of dark matter, okay, it's impossible that the dark matter mass can lie anywhere from about 10 to the minus 22 eV, which is an inverse year in frequency, to 10 to the 19 GeV, or in fact much larger. Okay, there's a huge range of possible masses of what dark matter could be. And there is a broad range of frequencies from about 10 to the minus 22 eV to about 10 to the minus 4 eV today, where there are a number of experiments like ADMX, Casper, or DM radio, things of that sort, that are probing dark matter in that regime. And you're of course aware of experiments like xenon, things like that for WIMP experiments that can probe dark matter at the 100 GeV range or so. But as you are undoubtedly aware, there is now a bunch of activity trying to look for dark matter between 10 to the minus 4 eV, let's say, and about 100 GeV or so. And this is an interesting region, right? Because if you think about it, how come we're able to search for dark matter with such an incredibly low mass and a very, very high mass here, but nothing in the region in the middle? What is the fundamental scientific challenge that you have to overcome to be able to probe dark matter in the region in the middle? And this is why the region in the middle is kind of tough, right? Because if you think about how an experiment like ADMX is trying to look for ultralight dark matter, it's not trying to look for ultralight dark matter by absorbing energy directly, right? Because that's too tiny. What you really do is that you have a coherent signal that's oscillating, and then you use that coherent signal to build up a current, okay, in some system, and that current is what you eventually measure. But to build up that current, you require the system to oscillate for quite some time. You require a coherence time. And unfortunately, this coherence time is inversely proportional to the mass of the particle. So for a low mass particle, that's great because you have a lot of time to build up your signal. But at high mass, the coherence time dies very rapidly, so you have no time to build anything up. At the same time, in this regime, the energy being deposited is so small that you cannot use conventional WIMP calorimetry as a way to go for dark matter in this particular regime.
So you're saying that for ADMS, Casper, gamma radio, they all rely on this coherence time?
They do. Yes. So one way to tackle this problem, this is not the only way, but one way to tackle this problem is that what you might hope for is that if you deposit a tiny amount of energy in this regime, you could require some kind of an amplifier that amplifies a small amount of energy into something that you may try to measure. The challenge, of course, is that you require a large target mass because you're going after dark matter, okay? And so you're looking at a very, very rare event, of course, because you're looking at dark matter. So not only do you need an amplifier that can amplify a small amount of energy, you also require this amplifier to be stable over a long period of time, over several years. So here's an idea, okay? And let's see how well it works. So here's the concept. So let me start with a magnet with all the spins in the magnet aligned in one direction. And let me now apply a magnetic field in the opposite direction. So now what I've done is I've placed every spin in an excited state. Okay? Suppose the following happens. Say the dark matter comes, it collides, it deposits some amount of heat. The heat will cause some of these metastable spins to flip. What's going to happen is that when the spin flips, it releases the stored Zeeman energy in the system. And the stored Zeeman energy can go nearby and cause the nearby spins to also flip. Okay? So this leads to what is called a magnetic deflagration or a magnetic burning of the system, where I basically deposit a tiny amount of energy and the energy release causes nearby spins to also flip. So this is how I think about this. Something scatters, there's a bunch of energy coming out of it. Okay? And this, of course, amplifies the deposited energy in the system. So it's a lot like a bubble chamber. And you can ask, is such a thing actually possible? Right? And what about stability? How hard is it actually to do? So this is where the topic of single molecular magnets come in, or really single molecule magnets. Because if I actually take a ferromagnet, this particular thing that I talked about, where I deposit some energy, the spins flip, and the release energy goes around, expanding around, doesn't really happen. That's because in a ferromagnet, the spins are strongly coupled. So when I flip one spin, it doesn't go to the neighbor and make that guy also flip. What you really want is weak spin-spin coupling. Okay? So each spins are independent and can wobble around without talking to each other too much. But at the same time, I cannot use something like a gas. A gas, of course, has weak spin-spin coupling, but a gas also has poor heat conduction. So when I flip one spin here, the release energy will not go to the neighbor and do the same thing. What you need is a system where there is weak spin-spin coupling, at the same time, large heat conduction. So what you require is something called an organometallic complex. This is just one example of something like this that could actually work. Where the basic idea is that there's a central metal complex, okay, which has spin, and surrounding that is some organic material. Okay? And that then accomplishes the fact that there is weak spin-spin coupling now because these guys are a little bit far from each other, and notice that the spin-spin coupling rises 1 over r cubed. But I have all this organic crap around me which is very good at carrying heat around. Okay? And the idea is that each molecule here acts as an independent magnet. Hence the name single molecule magnet. These are recently discovered systems. There are about a few hundred known examples of these things. And we can indeed make large samples of these objects. Okay? Where magnetic deflagration has been experimentally observed. So this particular phenomenon that I just talked about, where I take a system, cause some spins to flip, and the rest of the system burns, has been experimentally demonstrated. So what the chemists have done, this is discovered in chemistry first, is that they take one of these systems, apply a magnetic field, and usually what they do is just heat one part of that sample, and when they heat that part of the sample, the spins relax, and the relaxed energy goes forward in the system, causing more and more spins to fall. Okay? That's been experimentally observed, and is very well studied in one particular system called manganese acetate.
Sorry, so can I just ask, conceptually though, if you're needing the, can you just go back just for a second? So
Yes.
if you need the organic trap, as we call it, to conduct heat, why isn't it just conducting the heat away? Why?
It will do that too. So we will talk about what you need to make it happen. So that's in fact my next slide. Okay, give me a second. So let's understand the physics of this, exactly as what Marcus is saying, where I can just think about the system turns out in a two-level Hamiltonian, where without a magnetic field there are two metastable states, there are two ground states, spin up and spin down. Okay? And when I turn on a magnetic field, what happens is that the one state becomes metastable compared to the other, obviously. And the crucial point in the single molecule magnet systems is the fact that when this state has to decay to the ground state, it has to go through some kind of tunneling barrier, which exists due to the chemistry of the system. Okay? And you want to therefore realize that if I place the system, if I cool it down and all that and place it up here, the metastable state is very long-lived, right? Because there's decay through tunneling. And so this can be described with some kind of Arrhenius law, it's a phenomenological law, but we understand where it comes from. We basically say that the time scale for the decay is set by some intrinsic lifetime times e to the some barrier potential, which is the tunneling barrier that you have, over the temperature. So what you can realize, therefore, is that at low temperature, this particular state is very long-lived. But if I locally heat it, right, localized heating will rapidly decrease the lifetime of this source, causing localized decay. Okay. So when does this happen? So this is to answer your question, right? So let's ask this following question. I take this particular material, I take a slice of region lambda, and I heat that to temperature T. Two things can happen. One is thermal diffusion, which is the fact that heat is being conducted away from that region, which will cause that area to cool. The other is before the heat diffuses, the spin can flip and release energy. The crucial point to understand is that heat diffusion cares about how large of a size I made hot, right? It takes a lot longer to cook turkey than to cook small pieces of chicken, because the heat diffusion is a random walk, and thus it scales as lambda squared depending on how big the size is. While the intrinsic relaxation rate doesn't care about how big of a region you actually made hot, right? So if you take any system and you heat a big enough part of that system up to that temperature T, the spin flip will happen before the heat can diffuse out over there, and when the spin flip happens, the energy is released and your system burns. Okay? So that's really all you have to do. And this basically sets the threshold of the system, if you will, right? Depending upon the intrinsic relaxation time, T naught, tau naught, and the thermal diffusion time scale, etc., it tells you how much energy needs to be deposited in the system so that this particular process that I'm interested in actually happens. So you can think about U effective, tau naught, etc., and the thermal diffusion time scale as the threshold of these things.
So I'm so confused though, because this decay rate or this decay time here is just the well, I mean, if you want to get this to be a cascade, right? Don't you want the magnetic energy to release to heat up the next region over?
Right. You do.
And
So it depends on the magnetic
there has
field.
to be some sort of factor that accounts for the efficiency of that, right?
When you release that thing, the heat goes out, and that heat is what is going up.
So there's some time scale for that to heat up. So I'm confused about how that is different from the diffusion, because
Well, it's just that once you burn it up, right? That heat is in there. It's just going to slowly get out one by one.
maybe just go on. I'm still.
Okay.
I guess I'm still confused about it. But just
I mean, it is certainly true that the heat getting out is through diffusion, right? So what you need is the fact that before the heat can diffuse out, the energy has been released into these, phonons or whatever, and they're just slowly making their way out, slowly burning the system one by one. Okay. So there are known examples of these systems with intrinsic relaxation times around 10 to the minus 13 seconds.
The point, I'm sorry, so maybe I got the point, but the point is that this magnetic thing is sort of keeping the sort of driving this diffusion. It's not
The magnetic energy is
to,
driving.
It's not that you're trying to beat this diffusion time.
No.
You're just trying to keep it,
Burning.
make the total amount of energy. It's adding energy. To
That's
this
right.
thing.
That's right. That's right.
All, okay,
That's right.
I got
That's all it is.
It's not trying to increase the rate.
No.
Okay. I
Yeah.
got it. Thank you.
Yeah. Okay. So if you look at the list of single molecule magnets that are known, not all of their properties are measured because people don't really care to measure everything because they're just playing with these things. But there are plenty of examples of something where there are favorable numbers that suggest that you might be even able to reach something like 10 millieV of threshold energy. Okay, just in terms of what the chemists know. So we're excited and thinking about how we can probe these things. Okay, so let me rapidly talk about testability. Right. So if you think about this dark matter game, you're really worried about essentially, what are the backgrounds can come in and all that here. So if you think about it, at these low energies, right, the typical background you're worried about in a dark matter experiment is coming from high energy stuff, radioactive decays or MEV or whatever, right? So these are of course not fundamentally a background for us in the sense that we are interested in like very, very low energy things. So the radioactive event at MEV is not actually what we're looking for. And you can detect that MEV event using conventional means. You don't need anything fancy like what we're talking about in order to actually look at this, right? So the actual background that you worry about really comes from the fact that these MEV events at high energy can occasionally have forward scattering. Okay, and that's something that CDMS, for example, has seen. And that, of course, is suppressed because you're suppressed by the forward scattering amplitude to actually do this, right? So if you think about like low energy dark matter detection, the typical problems that you worry about at high energy are not there because you can veto one. But the main point is that these MEV events will constantly keep going off, and we have to veto it. We have to, if these MEV events constantly kept going off, your detector is constantly set off, right? So even though we know it's a one MEV event and it's not a problem for us, if these things go off all the time, it will overwhelm your detector and constantly you need to reset it. This is a problem for bubble chambers because they'll see these things go off as they lower the threshold, and they'll constantly keep resetting the bubble chamber all the time, right? So if you really work hard, you haven't done that yet. The typical sort of background event rate you're looking at will be something like 1 per 100, 1 per every 100 seconds. But you have to work hard to get that. So in the beginning, these certainly won't be that way. But anyway, what is the thought? How can you handle this? And there are only two ways of doing this, right? We don't require the entire crystal to flip in order to know something has happened. With precision magnetometry, if even something like a 100 micron cube of the system flips, you can see that with the squid, right? You don't need something. I don't have the entire centimeter cube thing flip to know that an event actually happened. And the cool thing about the system is that the fuel in the system is the magnetic field, right? So one thing I can do is that anytime something goes off, I can simply turn off the magnetic field. And if I turn off the magnetic field, I've removed the energy from the system, and whatever is burning just burns a little bit and stops. Right? So this way, I have prevented the entire detector from flipping anytime something actually happens. In fact, a smarter thing to do, and it turns out to be a lot easier as well, is that in fact it's very, very hard to grow big crystals. So what you may rather do is instead of growing one big crystal, you may just grow a lot of powders. So each powder size, let's say, is 100 micron cube or something like that, and you just put them all together in your detector. And if you did that, something goes on, you burn off just that one particular powder, which is about 100 micron cube in size. You see that in the squid, you're happy, but that flame is now shut off, right? So this becomes automatically a way in which you're able to preserve most of your volume when some background event happens without having to constantly reset this thing, right? That's anyway the goal of what we want to do. We haven't done any of it yet, obviously. So this is some science fiction about how all we can actually do with these various technologies, but it looks very interesting in terms of what you can actually do. So let me tell you about what's actually happening in Texas A&M with the real demonstration. So what Rupert did was to see if any of this makes sense, right? So far this is all this theory stuff. Does this actually happen in the lab? So we decided to use manganese acetate, which is a well-studied complex, right? And it turns out it doesn't have the most favorable properties in terms of energy threshold. Its known properties put you at capital MEV, okay? It's not where we want to be, but it's what we started studying. And what Rupert did was basically have a system where he had a Hall sensor, it's a way to measure a magnetic field. He had a sample, which was the manganese acetate thing, and he had one sample, and he had one system where he had a radioactive source next to it, and there was another system where there was just a sample and a sensor with no radioactive source, right? And he's just simply asking, is it the case that when this radioactive source goes off, do I see something happening in my detector? How stable is it? Does this deflagration actually happen? And here's what we found. Okay, I think they did it like 10 times or something. So what was seen was basically that they have these two systems. The blue one is a system without the source. The red line here is a system with the source. And what you clearly see is that when in the system with the radioactive source, you've got the fact that the magnetic field is constant for a while and then it jumps, which is telling you that the radioactive source produced something. It got absorbed in this material, and the deposited heat caused the system to flip its spins, changing the magnetic field, while the blue line, which is the system without the source, had nothing happening at all. Right?
This is a single crystal.
It's a single crystal. Yeah, exactly. And so this is proof that this thing actually makes sense. It's experimentally demonstrated now. Okay, you shouldn't get terribly excited because the manganese acetate crystal we used has poor properties to go to low. I mean, its threshold is high. It's about a few MeV or so. But it's interesting for us because somehow this goofy theoretical idea actually made sense, and we're now exploring new materials whose properties may allow us to go lower in energy. With that, let me move to my final topic, which is how one can try to do directional detection of dark matter with crystal defects. This is with these guys over here. And the basic problem that we are trying to solve here is the fact that in the next generation of dark matter experiments, we will basically hit a target from, we'll hit a background from the sun, right? That solar neutrinos will come and scatter in your detector exactly the same way like dark matter will do. And the question really becomes, how do you actually go beyond this background in the next generation of experiments. Okay. So the one thing that you can actually make use of is the fact that when the sun produces neutrinos, you know where the neutrinos come from, they come and scatter, they deposit energy, there's going to be a certain direction at which things are actually going to go and scatter, while when it comes to dark matter, it's supposed to be isotropic, and thus if you can veto on all directions that point to the sun, you're basically happy. The reason why this is hard is that you require a big target mass in order to be able to actually do all of this, and you need to therefore be able to achieve directional sensitivity at large solid state density, so that you're not building a gigantic detector that takes up the entire Earth or something, or very, very large volume. You want a relatively compact thing to be able to do this, and that means you need a high density that can be there in a solid. So what actually happens? Let's see if there's even a signal that you can actually go look for. So I take a block of material, I have dark matter or neutrino, whatever comes and scatters, it dislodges the nucleus, it goes forward. As it goes forward, it will do a bunch of damage in the detector. It will scatter a bunch everywhere over here. And there is now going to be a telltale damage cluster that is well correlated with the direction of the initial ion. It's a lot like shooting a bullet, right? There's going to be a hole that points to where the bullet actually came from. The challenge is that all of this damage is contained within something like 50 nanometers in your system. And so you really require some kind of technology that's able to resolve what's going on at the 50 nanometer scale. Okay? But if you could look at the 50 nanometer scale, there's in fact very clear evidence that there was actually a damage trail there. So to look at what's actually happening, we did a trim simulation where we put in a bunch of ions, scattered them, and see what they do. So what happens is that you push this ion forward, it goes and scatters, it creates a bunch of like lattice vacancies. That's the kind of damage it's actually causing. So it creates something like 200 to 300 vacancies and interstitials in your lattice. This makes sense because the typical lattice potential is about 30 eV or so. So with something like 10% efficiency, you're able to create some damage. Okay, and this is nicely correlated as well in terms of where this damage actually happens. But to see this, you require nanoscale measurements. Okay, so here's where the technology gets very interesting. So there's a technology called nitrogen vacancy centers in diamond, for example. So you take diamond, turns out, and then you create a bunch of holes in it, and those are the vacancies, and then you implant some nitrogen next to it. And if you remember your chemistry, there's an unpaired electron sitting out there. And what you can actually do in these diamonds is that you can shine lasers at these electrons, and they will cause transitions, and that is something allowing you to actually study the levels of that electron very, very well. Okay? So by studying the levels of the electron very, very well, you're actually going to be able to probe the local electric fields in that system at the nanoscale. Okay? So that's just a fact about these NV centers. That's why the people who worked on them studied them, because there's a way for you to really probe nanoscale physics of what's going on. Okay? And people have, for example, demonstrated NV centers in bulk diamond at a density of 1 per 30 nanometer cube. This, of course, wasn't done in a gigantic sample. This was done in a small sample, but at least proof of concept that actually exists. And these nanoscale measurements have now been experimentally demonstrated all around the world, and there is active development of sensors by many groups around the world.
So, sorry, is the concept that you're going to, this detector is going to sit there for a long time, you're going to get damage,
yes,
and then you're going to read it all out, and that's the end of the experiment.
That's how it works.
That's
yeah.
how it works.
That's how it works. Exactly. Yeah. And you may be skeptical that, so you can ask this question, the signal clearly exists, but then can you actually measure it as something actually existing? But you may also be like, well, diamond is very expensive, okay, there's not a diamond you give your wife, it's diamond that's industrially produced, but it's still pricey. Is this magic only true in diamond? The answer is no. This is true for a variety of crystals. For example, sodium iodide, which is used for experiments like Dalma and cosine, things of that sort, they actually have what are called F centers, which are very similar and can also be optically probed.
That's what my dad used to work on. So this is
good stuff. Right. So let's see what the physical effect actually is. So you smack something into this, there's a damage trail that actually goes in there, and the damage trail, what it actually will do, because these atoms are knocked off from where they are, they're going to create strain in the crystal, and the strain will of course shift some transition line in the system. Okay? And the strain, you can look at Hooke's law and see what happens, drops off as 1 over r cubed. And you multiply that by the number of vacancies in this thing that you're causing, something like 100 to 300 or so. So the strain that is caused by any, locally is 100 to 300 times whatever is going to go all over. So if you do the actual simulation and you calculate what actually happens, you find that because of this damage trail, the NV center line shifts by something like 100 kilohertz at 30 nanometers or so, while the natural line width is something like a kilohertz. Okay? So here is the main idea, right? Is that at the nanoscale, the signal to noise in what's going on here is a factor of 100. Which makes sense because I'm taking this bullet and shooting it. So locally I'm creating a lot of damage, but it's just in the nanoscale. So if I'm able to identify what's going on at the nanoscale with very, very high signal to noise, I can see what happened. So this is actually possible. So even a small number of NV centers can tell you exactly what's going on. So here's a detector concept that we have in mind. So we're going to take a large piece of diamond, let's say, or sodium iodide or whatever. We're going to make it the following way. We're going to segment the detector, which basically means that I take this thing and I cut it off in these sort of pieces like this, where the area could be large, a meter or whatever, but the thickness of each of these guys is only about a millimeter or so. I'm imagining creating this large density of these defects in there, okay, and then basically use conventional WIMP scattering ideas, for example, scintillation, ionization, etc., to localize interesting events. So if you think about the dark matter game, you're roughly looking at maybe tens of events in a year. And the dark matter guys can localize each of these events to something like a millimeter. Okay, that's something they can do. So essentially what you're then saying is that, okay, in a year, I have a bunch of these events, which I think are dark matter or neutrino events. I know where they are to within a millimeter or so. And what I'm going to then do is basically pull out those particular regions and study them very carefully. Right? So the way you can actually do that, it's kind of the reason why we had to segment it, is that if I just use conventional optical light within like a micron scale, I basically know where what's going on, because that's the optical wavelength. But then I of course want to get to the nanoscale. To get to the nanoscale, what people experimentally do is they apply a large magnetic field, so there's a big magnetic field gradient, and that shifts all the lines appropriately, and then you can use that to achieve what's called sub-wavelength resolution of what's going on. Okay? So that's also been done.
You have to surround, so basically you have to surround this by a very good dark matter detector.
Well, this is a dark matter detector.
Well, but this material, I mean, the noble gas ones, right?
Yeah.
They use the target as the thing that actually makes the signal, right? But these things will presumably not do that for you.
So you would require, for example, sodium iodide, which is another dark matter kind of thing, right? Where you just build, a big sodium iodide thing. So that's, of course, nobody's done that yet. Maybe cosine people like that may succeed. But if you do that, you then essentially have to do it in sodium iodide, right? That would be the idea. Actually, it turns out that this is not what we're going to do in practice, because we've learned a couple of new facts recently. One is that, for example, first of all, the main idea here, which is that when I do this kind of scattering, there is this damage trail. That has now been experimentally validated by people studying nuclear emulsions. So there's another technology where you have a bunch of thin films, and a dark particle comes and scatters, and then when the particle scatters, there's a damage trail. Okay? So the fact that this damage trail exists is now experimentally validated. Secondly, what we actually want to do is, instead of doing all this NV centrology, because we now know the damage trail is real, what turns out to be more interesting is, instead of doing this, you can actually take your crystals and scatter them with X-rays or electrons. So there's something called X-ray cryo-electron tomography or X-ray spectroscopy. So these are ways in which, once again, you're actually able to get to the nanoscale by just scattering particles off. So we got money to do this from the DOE, okay? And what we'll practically be doing is taking some object, shooting some neutrons at it, seeing localizing where this damage trail actually happened, and then exposing it to some kind of X-ray source and seeing if you can actually read it out. Okay? But you're right in the sense that to make all of this possible, you require a solid-state detector that is large. Okay? So we can't do this in xenon because if you scatter, the things will diffuse away too quickly. So one has to have a solid-state detector that is large, and if you have a solid-state detector that is large, you can then couple that with the fact that you roughly know where something went off and use these more modern techniques as a way to read that. So that is basically what we have in mind. Okay. So I'll quickly go through this because I'm way over time. And essentially what I would say is that both from what has been validated experimentally by these guys doing nuclear emulsions, as well as our own simulations, it does appear that with a few events we can actually get few sigma detection with things like this. With that, let me conclude. For me, it's very exciting to think about how we can actually probe the weakly coupled universe, because that's something we haven't done so far, given that there's a strong physics case for it, and I think that's a very exciting thing to do. Thank you.
Questions? Chase away the experiment.
I guess so, yeah. All right, thank you.
We still like you.
Oh, that's